All right, we have to do it. We have to do it. Okay, we have to do it. So, no, this is very good. Very good. Sorry, it's not that bad. We're going to talk about bases, right? And this is just a small piece here that's going to set up many, many good things. Of course, it will be about AX equals B, and in fact, the null space will come back. So, it's great, right? Very, very nice. Okay, so let's just, there's a little menu here. All your bases are belong to us. So, spanning sets for subspaces or vector spaces. So we had this yesterday, not yesterday, last time we talked about things, whenever you were watching things. So this was for the matrix inigo. And let me just go back. Inigo is here, right? This little matrix, 2 by 3. We found the column space and the null space. We're going to come back to it in the next piece. And the null space had these two vectors being the sort of cornerstones for it. That they naturally came out. They're not the only ones that could do it, of course, so we'll get to that in a little second, but they're the ones that naturally come out because there's one method for getting to null space. So here's null space right here. And we ended up with saying that it's some x, it's any x that's in 3 dimensions, that's that statement, such that x is some multiple of -210, and then some multiple of -101. And we can see from this, this is something that's quite deep and sneaky, is that this 1, 0, and 0, 1, it's the identity structure sitting there. There's no way we can make this vector out of this vector or vice versa. And that, as we end up with more and more vectors in our null space description, that becomes a more clear, powerful thing. So we need both of those vectors. That's this idea of a basis we're about to get to. But here we're just saying it's a spanning set in that this makes a subspace, right? So we can take any multiple of the first vector plus any multiple of the next one, and that traces out a 2-dimensional subspace of 3 dimensions. We have to get it all connected. And the 2 is the rank. That comes from the rank of the matrix. Great. All right, that's a spanning set. We want to show that it's a basis, which means that it is a minimal spanning set. It means that it is, we can't throw any of these vectors out. So we need to understand what those things are. You've been using a basis over and over again whenever you talk about I hat and j hat in 2 dimensions and then k hat for 3 dimensions. Okay, good. So we like these things. For sound waves, we have sines and cosines, right? We have Fourier transforms, and that's a basis for sound, for example. We use wavelets as a basis for pictures, lots of other things. And later on, we'll see that we can use bits of tartan from Scotland as a basis for pictures of any kind. Right. Okay, so just to go back to that was what we got to at the end of the last piece. So that's a big deal. And then we're going to get to bases, which are, as I said, the minimal spanning sets. And then there's this great piece here where we can say, oh, we know all about this because we know what we know about null space. So it's all going to be connected. Everything's connected. And then this last piece is very important, the dimension of a subspace. So we want to be able to find, say, null space or column space and these other 2 mysterious spaces that are coming, and be able to say this is their dimension, see that their dimensions are what they are. It's a big deal. All right. Okay, last thing. We've incorporated Melvin, the coarse difficulty dinosaur. So weeks are going along the bottom here. So we've traveled through, we're about here. And we're getting into the mid-region of the dinosaur. So things are slightly thicker. It will get thinner again here. Is it easier? Maybe, but it's also sort of less abstract perhaps, and more fun. This is the eigenvalue region of the dinosaur, just here, right? This is the LU, sometimes called the tail of the dinosaur, and this is the big picture section, tummy. Okay, and then the head is the SVD unit. Wow. I'm being secretly paid by Museum of History. That would be good, actually. If yeah, they should do that. So So I'm going to give you 3 examples of spanning sets for R2, right? So this is a vector space. We're not talking about a subspace. It's a vector space, just the good old plane, the infinite plane, which for some reason is actually being represented on this finite pad here. Okay, because we use our brains to make bigger spaces. So this is a spanning set. So it's just 1, 0, and 0, 1. And you will recognize them as, right, if you want, I hat and J hat. Good. And here they are, right? So we can take, and the idea is we can take any combination. Let me give it another color. So, right, we said some multiple of this one plus some multiple of this one to make any vector in R2. And there's no redundancy here as well, right? There's no, you should just at least visually see, we can't get to this point, whatever this one is, we can't get to here with any other arrangement of multiplying this vector and adding a multiple of this vector. There's only one way to do it. So it is a precise representation. So that's what we'll see as a basis, right? There's no redundancy. So here's an example with redundancy. Now we've got 3 vectors, and let's say we're trying to construct this one. So let's give them names. I'll go back here and say that this is actually, I want to annotate a few things on top. So let's call this one A1. Very suspicious. You should be very suspicious. A2. They look like columns of an A matrix. Craziness. This is going to be A1, A2, A3. All right, let's make it easy for ourselves and make the whole course about one thing. All right. It's not like calculus. Oh my God, it's disgusting. Okay, linear algebra. It's the best, people. Okay. Right. So I'm going to note these ones. So this is A1. Yep. Not lying. This is A2. And this is A3. Right. So just at least visually, we haven't done this mathematically, you could imagine we could multiply A1 by something and then get out to here, and then A2, right? So this is some combination of, and not use A3 at all. Or we could multiply A3 by something here and then add some amount of A2. So there's more than one way to get there. And yeah, or we could go all the way past and then add some negative amount to get to here. So there are many ways, right? And in fact, you should guess infinitely many ways to reach, to create this vector. This vector as a linear superposition of these other 3, right? Or a linear combination. Let us write all the words. A linear combination of A1, A2, and A3. Now, the third example, we're back to where we were, right? And in fact, this is a very famous kind of one, and we should see this pop up again. So here's A1 and A2. There's a 1 over root 2 out the front. So why is that? What is the length of these, of the 1, 1 vector? So note the length, and we'll write it like this, the length of A1 equals, right, this indicates length, we're going to come back to this. It's 1 over root 2, and right, you go across 1 and up 1. So it's a little right angle triangle, 1 squared plus 1 squared. It's a Pythagoras character. Possibly some Druids as well. Let's give the Druids a chance. I'm sure everyone figured it out. It's a crazy thing. So, and if you do that, we get 1 over root 2 times root 2 equals 1. That's why there's a 1 over root 2 at the front, because we've normalized it so that these are unit vectors. We like unit vectors very much because they just contain direction and not other information, right? Okay, so they make really good basis vectors. We'll be so thrilled to see them later on. So if you imagine these are sitting on a polydrawn circle here. So it's actually just a rotation of the basis vectors that we had over here, right? We just turn them around. Two vectors in R2, same story. We can only, right, there's only one. So let me say it for both of these. The two vectors pointing in different directions. If they're pointing in the same direction, it wouldn't work. So two non-parallel vectors give a unique representation of each point. So representation. That means something times the first vector plus something times the second vector equals the vector you're interested in, right? That you're trying to point to. Okay, infinitely many solutions. So we're getting there. Melbourne is a real champ. Okay, more things over here. So here are the words that kind of back up. So the first two examples are special because we have to have both vectors, right? And these spanning sets, right, the curly braces and then two vectors, it's just two vectors. You just hand over two vectors, right? We're not handing and say this, from this you can generate the whole space. That's a very important thing to understand, right? It's not the space, it's a very compact way to describe the space. You know, and some things are more complicated, right? You can't just hand someone the lexicon behind Moby Dick and say, knock yourself out. You can just make it a little more complicated. But we have linear superposition, so we're good with that. All right, so they're special because we need both vectors. Boom, boom. I'm just going to do this. And then two, we can take any one of those away and we'll still be able to span R2, right? Spanning R2 is this means that we can take all linear superpositions and reach everywhere. So if we got rid of this one, right, we just have I hat and j hat. If we got rid of this one, fine, right? They're not pointing in the same direction. And if we got rid of this one, we'd be okay too. All right, big deal. So the right words for what we've just said, I'll say these things. Right, so 1 and 3 have linearly, you say linearly independent sets of vectors. It means there's no, right, so we'll come back to this more and more and more with the big picture. We can't express one in terms of the others, for example. Right? We can't just throw one out. So that's what we could do here. We could say this A3 is A1 plus A2, so we can just toss it. Right? We don't need it, it's redundant. So that's true, and then, but we say that T2 is a linearly, or has a linearly dependent set of vectors. Linearly dependent, right? Set of vectors. That's an E there, to be clear. Linearly dependent versus linearly independent. Okay, good. So here is, so there's a whole bunch of, this is a big deal, definitions. All right, let's get it right. So we're going to say, very suspiciously, a set of vectors. A1, A2, that's not good. I'll put in a new, we need some more space. A set of vectors, right, curly braces, A1, A2, each one is just a vector, up to, let's say, AN, we have n of them. In Rm, right, we're just, for generality, we'll just say we're in some m-dimensional space. We have n vectors. That sounds, yeah, we know an m and an n we've had a lot. So this is a definition, is linearly independent. Linearly, I know, there could be more beautiful words, but right? The linear bit means that we're only ever multiplying things by real numbers, and we're only ever adding them together. There's no squaring or squelching or doing weird things, right? No splinching, right out. A set of vectors in Rm is linearly independent if this is true, if x1 times a1 plus x2 a2, let me see what these are, plus xn an equals 0 only has x1 equals x2 equals ... equals xn equals 0 as a solution. So what is this? What is this madness? So the only way to combine them is to get 0. It's a bit funny because we're going to define it this way. And I've got a hat where I shouldn't have a hat. Bad. Boop. We want to make 0. So the only way to stretch these vectors, right? You're allowed to multiply a vector by a constant. That's this x1. Let's make this clear. x1, x2, x, right? We're allowed to do that. Add them in such a way to come back to 0 is if we don't go anywhere at all. All of them are 0. So these are right. So these are clearly elements of the real numbers, right? Scalars. Okay. xi is a scalar. Just in brackets. Sneak that in there. All right. Good. Oh, so what is this? This means, so two things. So y, so first we'll do that. So let's do y. Why use this notation? It's a bit funny. So that is a thing. We're just going to make that a thing. A good box. Maybe it's not a good box. And then, so y, if, the story is that if, capitals people, if 1 xi is not equal to 0, right? If we're allowed to do that, then we can, right? So one or more of these, right? If one or more, then we can express one vector in terms of the other. Express one vector in terms of the others, right? You can put one on the other side of this equation here, right? We could put one over on the 0 in terms of the others. Whoop. Terms of the others. This is really nice. Okay. Okay. Does it? So hopefully that makes sense. So, so our example. So example 2. This guy. We could say 1 1. So I guess I should do it like this. We clearly have this, that 1 1 equals 0 1 0 plus 0 1, as I said before. So this is, let's put the red on them. This is A3, this is A1, and this is A2. So the notation for that would be, we'd have 1 times A1 plus 1 times A2 in terms of this definition minus A3 equals 0. 1 times A3 equals 0. Right? So there's a set of x's that are non-zero, right? So this is x1, this is x2, and this is x3. Okay, so let's see. So what are we doing here? This is the column picture. Huge, huge. This is, I want to write it, make it really clear, and we'll do it on the next page. This thing is the null space problem. Wow. Right, it's A, if we put the A1s and A2 into the columns of a matrix, call it A, x equals 0. Yes. Victory. Okay, so that's a total victory. So we, right? So so we're going to say, okay, so seeing things. These AI, right? A1, A2, AN are linearly independent. This is this definition, are linearly independent if is the same as saying, right, equivalent to saying this matrix A, A1, A2, it's 1, A, N. This is an M by N, and it's our matrix A times X. This is an M by 1 equals 0, has only X equals 0 as a solution, right? It's the only solution, which is the same as saying the null space of this matrix A, let's call it A, awesomeness, A. Well, I don't like where that arrow is. Let us put it here. This is out here, A. The null space of A is equal to the 0 vector. It's good, right? We've made it very easy. So if someone says, there's this term, right? There's this linear independence. I want you to test if these vectors are linearly independent. You solve for the nulls. You put them, stack them up next to each other, make a matrix, and solve the null space problem because it is the same thing. Okay. New definition. Let's just calm down. It's very exciting. It's very exciting. But let's just capitalize enormously. Ooh, so exciting. It just has to be noted here. So exciting. So definition. A spanning set. So if we have a spanning set, right? This is a set of vectors. A spanning set that is linearly independent. We can't make one of them out of the others, is called a basis. And this is a big word for us. It's called a basis. And the plural, you can have more than one, right? These two here, whoopsie, these two, they're both bases for 2 dimensions. Plural is bases. And that's not just with a funny accent. That is, right, bases. Ooh, maybe, let's do that. Bases. Right. Like the Bee Gees. Bases. Okay. Good. Right? Good? Not basises. Although that is fun to say. Or basin. Okay. Base octopi. No. Important point, actually. Octopi is, it does give people a sense of purpose when they say that, but it really should be octopodes because Greek. Okay. Octopuses, though, is much better to say. All right, so it matters. All right. Okay, so important. So that's a big thing. That's a definite. This is huge. Bases. Boop. So a definition. So a little note on that is bases are not unique. Right? They're not special. Just as we said, not unique. See examples 1 and 2. 1 and 3. 3. Above. Good. I hope we've got that idea. But some bases are awesome. Yeah, it's a little rough. Some bases are better than others. Right? They're more appropriate for the thing you're working on. There's a place for every basis. It's okay. Some are better than others, and some are just awesome. Some are, I think the technical term is totally awesome. We'll get to that. Yeah. Okay. So bases are really good because of this uniqueness, right? They have so bases aren't unique, but they give you a unique representation. General goodness is bases give us a unique representation of every point in the space that they span. Right, so that's useful. It is useful to have redundancy as well, so that's fine. But this is a good thing. So unique representation of every point, right? Okay, and then the last thing I think for this section before we go into, we'll go back to inigo and look at look at column space and null space for inigo, and figure out the basis story there and their dimensions. And then more generally, what the dimensions are for column space and null space. We've been saying we've been making claims, but we need to back that up with the proofy things. I have to make it more proofy, I think is the correct Buffy kind of way of saying that. Okay. The most important show ever. Right, here we go. So I think I just want to say this. Yeah. Yep. This is all good. This is really huge here. This is a great thing. So just to say it again, linear independence of a set of vectors, boom, is the same as saying that this matrix times x equals 0 has only x equals 0 as a solution, and of course that is saying that the null space of A is just the 0 vector, and we're totally happy with this. So this is the last piece for this section. Definition. The dimension of a space, whatever it is, subspace, the dimension of a space is the number of vectors. The number of vectors in any space, in any basis for that space. Huge. That is a big deal, right? Good. Dimension of a space should make sense, right? So the dimension of R2 is 2 because that's a basis. That's a basis. This is not a basis. We can make it into a basis. That's important. We can make it into a basis. We could figure out how to trim one off. So that can be a strategy we can we will come to later on. Let me just annotate this. So I'm just going to say this is a basis, not a basis, and a basis. So this is kind of like science proves that two-dimensional space is two-dimensional, and that's kind of what we've done here. But that is something that's less obvious when you've got some column space in 33 dimensions with a bunch of vectors and right? So, okay, I'm going to put that thing down, and I'm probably going to go and pat the cat, which, if that's available to you, you should do that as well. Bases, linear independence, linear dependence, spanning sets, and dimensions. Fantastic.